Hello and welcome to our project. Our project was a meteorological-based strawberry yield forecasting, and my name is Jason Meyer.
I'm Spencer Stiteman.
I'm Stephen Aradre.
And I'm Taylor Manini.
Here's our table of contents. First is our introduction and background information. After that, we'll discuss our analysis, followed by our results, and lastly, our conclusion. California's unique climate makes it ideal for growing various specialty crops. California is home to over 400 specialty crops, many of which cannot be grown anywhere else in the United States. The climate-specific locations where these specialty crops are grown show how sensitive these crops are. One specialty crop that is grown in California is strawberries. California's climate is ideal for growing strawberries due to mild temperatures with sunny days and cool, foggy nights. California is able to produce strawberries year-round thanks to the 5 different districts along the California coast that produce strawberries. The 5 different regions of California in which strawberries are grown are Watsonville, Salinas, Santa Maria, Oxnard, Orange County, San Diego, and the Central Valley. In 2019, California was responsible for approximately 91% of the strawberries grown in the United States and totaled approximately $2.2 billion in value. That statistic shows how tremendous the size of the California strawberry industry, along with showing how valuable the California strawberry industry is. Specialty crops are incredibly important to California's agriculture as well as economy. The value that strawberries hold is very important when it comes to making growing decisions and business decisions. If proper decisions are not made, entire fields could go to waste due to poor planning for weather or having a shortage of labor. Increasing weather variability has made the need for an accurate forecasting system even greater than in the past. Weather variables have always been a concern of strawberry producers, but now with climate change and even more variable weather, the need for an accurate forecasting system is greater than ever. Producers have looked into forecasting tools in the past, but there has yet to be one that is accurate enough to be useful. As weather variables become more extreme due to climate change, the need for an accurate forecasting tool is on the top of many producers' lists. Losing an entire field of strawberries could be devastating to many producers, and an accurate forecasting tool would help them to mitigate that risk. Certain weather variables can be very detrimental to strawberry crops. Some examples of these weather variables are wind speed, precipitation, radiation, and temperature. Producers pay close attention to these variables because of the extremely high value that strawberries have. Next slide, please. Along with changes in climate affecting strawberry production, changes in industry have been taking place as well. The strawberry industry is becoming increasingly more concentrated, leading to producers in California growing more strawberries than ever. As growers expand their current growing areas, they will want to make sure that they're increasing their yield and making profit by expanding. An accurate forecasting system will be incredibly useful to make sure they are growing efficiently. Next slide, please. One possible forecasting tool that could be useful to producers is a regression model that accounts for different weather variables and accurately forecasts strawberry yield. Our group has been working with Good Farms, a strawberry producer in Santa Maria in the Salinas-Watsonville area. Santa Maria and Salinas-Watsonville area both have great climates for strawberry growing. The climate is fairly mild with lots of coastal fog to provide cool, wet evenings and mornings. Good Farms asked our group to try and see if we could make some sort of forecasting tool for them in order to see if they could increase their yield. After looking over the data that they shared with us and doing research on our own, we decided that a regression analysis based on weather variables and daily yield would be the most useful forecasting tool for Good Farms. We hope that our regression analysis will help producers in the Santa Maria and Salinas-Watsonville area to make more informed management decisions. Along with using the data from Good Farms, we also use publicly available data so that any producers in the Santa Maria and Salinas-Watsonville area can utilize our tool and make informed decisions themselves. Next slide, please. Before we begin discussing our own strawberry forecast model, we want to discuss the existing strawberry forecast models and where ours fits among them. Lobel in 2006 created a statewide yield forecast regression model that related temperature and precipitation to statewide yield. Although helpful, yields vary widely between districts, and aggregating yield at the statewide level is far too broad for many producers to find useful. In 2016, HATAC developed a meteorological-based district-wide yield forecast model that included 9 meteorological parameters, but excluded many weather variables that are significant in affecting yield. Finally, in 2021, Abd al-Rahman created a forecast model that incorporated imagery data in addition to meteorological parameters and used an individual producer historical yield to forecast future yields. Although this model is extremely accurate, producers without access to intricate imagery data cannot use it. Therefore, there is a need among producers for a district-level forecast model that includes all the significant meteorological parameters that affect strawberry production. Here's Taylor to discuss the materials and methods that went into developing our forecast model.
Analysis materials. So to perform our research, we have collected various data. The first is district daily yield data from the California Strawberry Commission, where we used the years from 2012 to 2020. Next, we used meteorological data from CMIS, also known as the California Irrigation Management Information System, which are weather stations close in proximity to strawberry farms in the Santa Maria and Salinas-Watsonville districts, where we also used 2012 through 2020 data. Lastly, we used Good Farms production data in Santa Maria and Salinas and Watsonville for 2020. Next slide, please. Regression analysis methods. So we performed multiple linear regression analysis, and this relates specific meteorological parameters to yield. It also helps to develop equations that predict yield given the values of selected meteorological parameters. And then we came up with monthly regression equations. These regressions were ran by month to account for the systematic changes in strawberry production at different stages throughout the year. And then with that, we decided to do a 3-week lagged weather data. And daily district yield was matched with meteorological data from 3 weeks subsequent to account for the short-term weather effects on yield. So as an example, the daily yield on April 21st would be matched with the meteorological data from March of the 31st. Next slide, please. Correlation analysis methods. So correlation matrix. This helps determine the relationship between a selected meteorological parameter and the relationship to yield for each district. The matrix is broken down by month due to certain meteorological parameters having varying relationships with yield at different times of the year. Next slide, please. Cross-validation analysis methods. So cross-validation is a statistical method to determine the accuracy of regression model at predicting daily yield given values of meteorological parameters. So there were 2 methods of cross-validation used. The first was holdout. This approach was to determine the accuracy of predicting district-wide daily yield. And the second was Good Farms approach. And this was determine the accuracy of predicting daily yield at an individual producer level. Next slide, please. To continue with cross-validation, we will talk about the holdout approach, and this was used to evaluate accuracy of the regression model at predicting district-wide yield. And for the training data set, the daily district yield and weather data from 2012 to 2019 were included to develop our regression model. And then to hold out, we took out the 2020 data for this part. And then testing the data set, expected daily district yield in 2020 calculated by using regression equations and meteorological parameter values from 2020, then compared with the actual daily district yield in 2020, which was held out from the original model. And then for the Good Farms approach, this was used to evaluate accuracy of the regression model at predicting yield at the individual producer level, and the expected daily district yield in 2020 calculated by using regression equations and meteorological parameter values from 2020. And then this was compared with the Good Farms actual daily yield of 2020. And now Jason is going to speak further upon the results of all of this.
And now we come to our regression analysis results. For our regression analysis, we conducted 9 individual regressions that yielded 9 individual regression equations by month per district, ranging from April to December when production is significant in both districts. The meteorological parameters included in each regression equation, seen in the graphic below, are evapotranspiration, precipitation, solar radiation, average vapor pressure, maximum air temperature, minimum air temperature, average air temperature, maximum relative humidity, minimum relative humidity, average relative humidity, dew point, average wind speed, wind run, and average soil temperature. The general form of each regression equation is y equals c plus m1 times x1 plus m2 times x2, and so on, where y is the predicted daily yield in pounds per acre, c is the equation intercept, m is the coefficient corresponding to a specific meteorological parameter, and x is the value of the specific meteorological parameter of that day. Below are the regression equations by month and per district that follow the general format previously outlined, with the Santa Maria District regression equation shown first, followed by the Salinas-Watsonville District regression equations below. To use these equations, a producer would first decide what day they want to forecast, refer to that month's regression equation, and then retrieve the California Irrigation Management Information System's weather data from 3 weeks prior to that date and plug in the variable values to that month's equation. And now we'll be moving on to our correlation analysis results. For our correlation analysis, we found 14 different correlation coefficients for each meteorological parameter related to yield, divided up by month and by district. We divided our correlation analysis up by month because some meteorological parameters have different relationships to yield at various times of the year, thus allowing the producer to see the correlation between a specific meteorological parameter at a specific time of the year, rather than assuming the relationship is constant throughout the year. Positive correlation coefficients can be interpreted as if the selected meteorological parameter increases in value, yield also increases, and if the selected meteorological parameter decreases in value, yield also decreases. In turn, negative correlation coefficients can be interpreted as if the selected meteorological parameter increases in value, yield decreases, and if the selected meteorological parameter decreases in value, yield then increases. Also, correlation coefficients that are in between negative 0.1 and 0.1 are insignificant to yield and should not be considered to have a correlation with yield. Below are the correlation matrix for the Santa Maria District, followed by the correlation matrix for the Salinas-Watsonville District that are each divided up by month, ranging from April all the way to December. Next, we move on to our first method of cross-validation analysis, which is often called the holdout approach in statistics. The holdout approach is used to determine the accuracy of our model at predicting district-wide daily yield. To recap, the holdout approach uses the daily district yield values from 2012 to 2019 and the weather data from 2012 to 2019 to generate a regression equation that can be used to predict the 2020 expected daily yield and cross-reference that with the actual daily district yield in 2020. Below are the results of the holdout approach, where the orange line is the expected daily district yield for 2020, and the blue line is the actual daily district yield in 2020. On the left are the results of the Santa Maria District cross-validation analysis, followed by the Salinas-Watsonville District cross-validation analysis. For our second method of cross-validation analysis, we found the actual yield data in 2020 of Good Farms, a producer with locations in the Santa Maria District and the Salinas-Watsonville District. This method of cross-validation was conducted to determine the accuracy of our model at predicting yield at the individual producer level rather than at the district-wide level. This data is paired with the expected daily district yield stemming from our monthly regression equations, with the orange line being the expected daily district yield in 2020, and the blue line being the Good Farms daily district yield in 2020. On the left are the results of the Santa Maria District cross-validation analysis, followed by the Salinas-Watsonville District cross-validation analysis. It's clear from the cross-validation analysis that our model is much more accurate at forecasting yield at the district-wide level rather than the individual producer level. Here's Stephen to discuss the main findings, limitations, and extensions of our regression models and project.
Finally, we have the main findings section. Our primary objective of the study is to give producers in the Santa Maria District and Salinas-Watsonville District an equation that forecasts daily strawberry yields based on the historical district yield data and historical meteorological data, with the ultimate goal is that producers are able to use these models to better predict supply, which would enable the operators of the companies to make better management decisions. For our first finding, we found that using district-wide yield data is effective at drawing a relationship between strawberry yield and meteorological parameters, but it lacks the ability of producers to accurately forecast their own supply operations. Individual producer factors playing a role include the fertilizer they use, which there's many ones on the market, irrigation schedules, which every farm can be different, and labor. Our second finding was systematic factors affecting strawberry production yields beyond weather variables. It is very possible to have the same weather values in different parts of the year, but the certain stage that the strawberry is in and the planting date will ultimately play a greater role in the production yields. Next slide, please. So limitations. Our first limitation is the dependent variable in our model is district-wide yields. Individual producers play a vital role affecting the yields, but since we are analyzing aggregated yields per district, these producers are all grouped together in one lump sum. We are unable to account for individual producer decisions. To fix this, the producer should use their own historical data yields that they have collected over the past couple years to get a better understanding. Our second limitation is systematic changes are not accounted for in our model for strawberry production stages throughout the whole year. We decided to split our data up by month to run our regressions, resulting in arbitrary results since there is no real difference from the end of one month compared to the beginning of the next month. By splitting this up into 9 different months running from April to December. Our third limitation, simplicity relative to other strawberry forecast yield models. Models with machine learning and imagery data along with meteorological parameters enable producers who have intricate data to have more accurate forecasting than producers without intricate data. Next slide, please. Extensions. Our first extension is the ability to count for systematic changes in strawberry production at different stages throughout the whole year, resulting in a single regression equation that can consider our meteorological parameters and consider systematic changes in production. Our second extension is historical yield data from individual producers. If we were able to obtain historical yield data from an individual producer, it would enable us to more accurately predict individual producer yields instead of using district-wide data obtained from the California Strawberry Commission. The district data is a general overview of the whole strawberry production throughout the state. By using producers' own historical yields, it would give them a more detailed and up-to-date yield forecasting. This would be very beneficial for these farms in case they had a drastic changes that happened over the past couple of years, and they could see day-to-day operations and see the outcomes that this affects their supply forecasting. Our third and final extension was meteorological parameters will continue to play a vital role, but if we could include additional variables that enable us to account for systematic changes in strawberry production at various stages of the year. Next slide, please. Thank you. Overall, we learned a lot about the ever-changing industry, and we are happy with our findings from constructing this senior project. We hope to assist others in the future who are able to use our data to test their hypothesis and or benefit their work on the given subject. Next slide, please. These are our sources.